Assalamu alaikum. In our last couple of videos, we have been studying about inverter switching characteristics, which include the capacitances or input output capacitances, and we have also seen the load capacitance as well. And in our second video of this series, we have studied about the rise times and fall times, how they can be calculated, and also how they limit the the frequency of our circuits or speed of our circuits. So now in this session we will study about what is the propagation delay of our circuits. Normally the propagation delay is time required for signal to travel from input to output, from input gate to the output terminal. So we have to calculate and we have to derive the expressions for this propagation delay. And secondly, in this session we will study how the load capacitance can affect the rise and fall time of our circuits. Because the load capacitance is basically the capacitance which is basically appear at the output. And at the end of this session we will study how the power dissipation affects, what factors are involved with power dissipation. We have two types of powers here. One is our DC power and the other one is our dynamic power. We have to see what these two factors are and how they are related to each other. And similarly we will also see that how the fast circuits affect the power dissipation. Is there any link? If we have a higher frequency circuit, then what will be the power dissipation? Either it will be higher or lower. So let us start with the propagation delay, where we will investigate what are the equations for propagation delay.
So we have to solve the expression for propagation delay first. We have to solve it for this propagation delay. It is a delay between input and output, and we can also say it as a reaction time. It is a delay between input and output, and obviously it is known as reaction time. So to define our propagation delay, we have two different quantities. These two quantities are TPF and the other quantity is TPR. The TPF and TPR, these two quantities basically are the time when our voltage reaches from VDD or from 0 volt to VDD by 2. We can say that TPF implies that TPF is a time when our V out reaches it reaches VDD by 2 from it's a fall time, so we can say that VDD by 2 from VDD. And this this was TPF, and this we have TPR. V out reaches VDD by 2 from 0 volts. We can draw it in this the waveforms here. We have our input wave, this is our time t, this is our V in, and if we draw this wave here, we will get something like this. It goes to high level and then goes back to 0. And correspondingly, if we want to draw this the output expression here, the output expression would be V out and Vt, and we can draw it like initially it was at 0, and at this time and at this time the voltage is changed. So at time 0 it was VDD, then it goes to, let me draw it a bit more here. It goes to 0, and after some time it goes to a high value. So we want to know a time when this voltage crosses this VDD level, like it crosses this level. This is our VDD by 2. So we can say that this time here, like from this point to this point, this is known as, this is like TPR, and this is TPF, and from like this point here, when this voltage starts rising, I guess I should make it a bit wrong here. So it's something like this. So when this voltage, like at this point and at this point, this delay here, it is known as TPR, because it is representing rise time here. So the average propagation delay can be written as like average propagation delay. It can be written as like TP is equal to TPF plus TPR divided by 2. So we can average these two quantities and we can find the average propagation delay. And like from equations, like we have our equations for the rise time and fall time, the F and TR. We can like find the actual value of like our propagation delay. For example, we had this expression here, Tf was equal to tau of n ln of like VDD divided by V out, and we have T of R is equal to tau of P ln of VDD divided by, this expression was divided by VDD minus V out of T. And similarly, if we put the values like in expression here, in this expression, we would eventually get to like the TP, we don't have to put the values here, but we have to find for the TPF and TPR. So for TPF, we will get the value that is ln of 2 tau of n, and for for our value of TPR, we will get like tau of P ln of 2. And how we can get these values here? Because we know that we can solve this expression like for our fall time. We know that the voltage changes from VDD to VDD by 2, and for this rise time it changes from 0 to VDD by 2. So we have to put the limits here in this expression here and here, so we can get the value. We can get these values here. So the final expression of our propagation delay would be like this, would be TP is equal to 0.35, that is like tau n plus tau p. So this is our final expression for propagation delay, but this expression is known as like this is a basic information, like this expression provides basic information like of delays in logic circuits. So this was a bit general discussion for, or like this was our discussion for propagation delay. How can we find the delays in our circuits? And what we have to do is we have to like apply some different some calculations from for our general discussion about the load capacitance and rise and fall times, the understanding of the load capacitance and the dependence on rise and fall time of for our device. So we have to look for like load capacitance and rise/fall times. So for this, initially we know that our output capacitance is given by like CMOS plus C load. Like this is capacitance, and this capacitance is because of our MOSFETs, and this is our load capacitance. So we know that the formulas for rise and fall times were given by like this was like TF was given by 2.2 Rn, and like we have written it earlier, something like Rn C out. So this C out now can be written as 2.2 Rn into CMOS plus CL. So we have to add the load capacitance here. Or if we simplify this expression, like we can write it in terms of 2.2 Rn C like MOS plus 2.2 Rn CL. We can define two terms here. This one term, this represents like this is our TF naught. This basically implies the fall time with no load, when there is no load at our output. So this represents the fall time for our no load condition. And we have another quantity which is like this one, 2.2 like Rn. This basically provides the slope of our line when we plot this TF with our load capacitance. So we will see in our diagram here, the graphs here a bit later. And similarly, we can solve this we can write it for the rise time as well. That is 2.2 Rp and CMOS plus CL, and we can write it as 2.2 Rp CMOS and plus 2.2 Rp CL. Obviously here this expression is also no load TR, and obviously it is also represented by TR naught, like when there is no load at the output. And these two quantities here, like one quantity is this one and the other one is here. These two quantities can be represented by alpha n is equal to 2.2 Rn and alpha p is equal to 2.2 R of p. So these quantities, these two quantities basically represent like the slope of our line when we plot CL with this TR. So the final expression can be written as like these two expressions, TR and TF. These two can be written as TF is equal to TF naught plus alpha n CL, and sorry, this is TR here. TR can be written as TR naught plus alpha p CL. So we have these expressions here, and we can plot this expression on a graph to like understand what would happen if we increase the load capacitance. So for example, if we have like no load situation, like for CL is equal to 0, so at CL it is equal to 0, or TF would be equal to like TF naught and TR would be equal to TR naught. If we want to plot it here, like we can say at 0 values, 0 conditions, when there is no load, TF naught, this point represents TF naught and this point represents TR naught. And so I forgot to mention, like here we have CL and here we have our time. So if we increase our CL, this this line increases linearly, and also this line increases linearly as well. So slope of this line is given by alpha p, because this represents the rise time, and slope of this line is equal to alpha n, because obviously this represents the fall time here. So like seeing this graph and these expressions, we can say that if we increase the load capacitance, the fall times TF and the rise times also increases, and obviously that increases linearly. So if we increase the capacitances at the load capacitances, then the rise time would be increased like in same manner. So now we have to discuss about the power dissipation, like how our power is dissipated in our CMOS circuits. We can say that for a CMOS gate with power supply VDD and current IDD, the power dissipation could be given by the multiplication of both these like VDD and ID. But if I write it something like here, I have this CMOS circuit here. This is connected to ground. Like this is our full circuit, like which includes pull up network and also pull down network. And the current flows here is represented by IDD, and here we have VDD. IDD means the current that basically originates from our VDD voltage. So power is given by like E is equal to VDD. It is multiplied with IDD. So this is multiplied with IDD, and we know that this expression is constant. Like this doesn't change, but this like the current, basically current flow, obviously this current can be varied, like this could be different, because this depends on the configuration of our circuit, how our circuit behaves. And similarly, we can say that this power, like this power here, it can be written as two terms here. Like one is PDC and the other one is P-dynamic. PDC means fixed power, or we can say that this is our DC contribution. And similarly, this is our dynamic power switching. Like this power, the dynamic power, this rises because of the power switching in our MOSFETs. So to understand this, we have to look back at the voltage transfer curve. So the VDC was given as it was drawn something like this, where we have on x-axis it is Vin, on y-axis we had our Vout. So we assume a case when, like case 1, when our input is stable at low voltage, like Vin stable at 1, like it is stable at VDD. So it is stable at 0 volts, like it is stable at the 0 value, like 0 volts. So like initially the output was equal to 0, output was equal to 1. So the graph could be drawn as what we have been drawing earlier. It could be drawn something like this. So it reaches the VDD value here. So we can say that at this point the NFET, like our NFET is off and PFET is on. Like our PMOS is conducting but NMOS is not. So we have to say that in ideal situation, IDD is equal to 0, but this is not the case. Because there is some leakage current which exists, and is known as IDDQ. Also, this can be represented by quiescent current. So this was the case when we are talking about the input voltage, like that is 0 volts. But what happens when the voltage starts increasing? We had discussed earlier in this VTC curve here, like when our voltage starts increasing, we had a linear line here which basically corresponds to our VM here. This line crosses VM here. So at this VM point, our NMOS and PMOS both were conducting. So we can say that there was a direct path between our the VDD and ground. So the VM is equal to, this VM represents our midpoint voltage. So we can draw the graph something like something like this, where we have our input voltage, we have here this current here, that is IDD. So at time when we had no voltage, like Vin is equal to 0, we had a current that is known as IDDQ. But when we increase the voltage, the current starts increasing because both our MOSFETs starts conducting. So we can say that at some point this reaches a peak value, and what that peak value is, that is our case 2. So we have to know what this value is, at what point this reaches our maximum value. So like we had said earlier, this value would be like this value when it reaches a peak value here, and then obviously this peak value comes out at Vm, and this current is known as I peak, like peak current. So like we can say that IDD reaches a peak value like at what, at Vm, and is given as IDD is equal to I peak. So the peak current occurs at this point. And we can also say that like at this Vm, both PMOS and MOS are conducting. These both MOSFETs are conducting. So the current reaches at peak value. But what happens in third case, like what happens at point 3, when like Vin starts increasing, like beyond like Vin increases from Vm. So what happens at this case? Our current starts decreasing again because there is no direct path between VDD and our ground. So like we have a discharging current, and there is but there is no current like from VDD to VDD to ground. So our voltage starts decreasing. So we have this case here, and it decreases to a value that is equal to like this IDDQ. So again we have the same voltage at output. So we can say that in ideal systems, when input is stable at 0 or 1 volts, power dissipation could be given by like in ideal systems, we can write the power dissipation value as in ideal systems when our voltages are stable at 0 or 1 volts, like voltages are stable at 0 or obviously 1 volts. So the power dissipation could be given by like PDC is equal to VDD and IDDQ. Like this is we know that this is our leakage current. So we can write these expression here, and normally this value is in pico amperes. So this value is in normally pico amperes. Obviously that is pico ampere per gate. And like we can say that this quantity is very small, because like this value here, that is in picoampere. So to find the dynamic power dissipation, we have to consider a case when we have a signal at input, a square wave that has a period of like t. So we can say that for dynamic power dissipation, we consider a signal, that has a period with period is equal to t, and obviously the frequency of the signal is given by 1 over t, and we can draw something like this. We have this signal, the maximum value is VDD, obviously this is represented by Vin, and we have time here, our signal is like this one here. We increase the signal, then the signal is decreased, and then we have this point here as well. So we are considering a case when we have to consider two cases here, when the signal is like 0 and when the signal is like 1. We know that this is our t and this is represented by t by 2 here. So we have to consider two different cases. Like first we have a case when when our input is low, low input. Then we can say that Vin is equal to 0 and PMOS is on and NMOS is off. Like at this case, when Vin is equal to 0, this implies that PMOS is on and our NMOS is off. So what can we do? Like the simplified circuit, like simplified NOT gate, can be drawn as, like we know that this is our conducting gate and we have another gate that is not conducting here. So we can draw it something like this. Like this is not here. So we can draw it something like this. We have Vin here, we have VDD, and what we would have here is we have a Cout capacitor. So this capacitor, obviously it will be charged. Like at this condition, the current will flow like from VDD and would charge this capacitor here, like in this direction. So like we can say that the direction of current is like this current, this IDD current flows from VDD through like Cout and to the ground. And we can say that this capacitor would be charged full to VDD, and the charge stored in this capacitor can be represented by like Q of E is equal to like Cout and VDD, because the charge stored in this capacitor is VDD. So in the second case, like in second event, when we have our input is equal to 2, like now we have to talk about this second event, when our input is equal to VDD. What that means is, like when our input is VDD, this implies that PMOS is off and our NMOS is on. So we can draw it a different circuit now, where we have this PMOS is now cut off, but we have our NMOS here which is turned on. So we have our input here and this capacitor was here earlier, and we know that this capacitor is charged at VDD value. It was at VDD. So now what would happen is, like this capacitor will start discharging from this path. So the current will flow from this capacitor towards the ground, but obviously through this NMOS here. So we can say that like the capacitor would discharge, like the capacitor would fully discharge here. Discharging happens and the voltage Vout eventually goes to 0. So what we can observe from these two conditions, like when our V input was 0 and when our V in is equal to 1. So we can conclude that there is an indirect path between VDD and ground, like obviously for our full scale input. So indirect path exists from VDD to ground in a full like in a full cycle input, because we have seen that in case 1, when our input was low, the capacitor charges at its full value, like VDD current flows to the capacitor, and then when our input goes high, the capacitor discharges to the ground. So there is an indirect path, the current flows from VDD to ground. So the total power dissipation, like in a single cycle, can be given as the total power dissipation is P average is equal to VDD, obviously IDD, but we can write it as we know that this I is given by we should know that Q is equal to I of T. So we can write that VDD and Q of E divided by T, and T here represents time period. So if we replace the QE values here, we know that the QE, what the QE is. So if we replace QE, then PAV will be equal to VDD square C out and F. We replace this T by F here. So the total power would be given by, this is our this is not AV, this is dy, dynamic power. So the total power, which we have been talking about earlier, when we saw that the total power was equal to DC power and the dynamic power. So the total power is given by P is equal to VDD, we had IDQ, and plus we have VDD square C out and F. So we can say that this term was very small, and from this expression we can see that this term is dominant. So this is a dominant term here, and what we can say here is this power, if we ignore this term here, this power is basically directly proportional to the frequency. So fast circuits, if we increase the frequency here, the fast circuit dissipates more power than a slow circuit. It means that if we double the switching speed, we would obviously the power will be doubled as well. So if we write it in words form, we can say that fast circuit dissipates more power, and obviously more power than a slow circuit. And obviously if we double the switching speed, this implies that we would double the power as well. So what we have observed here is our power dissipation depends on our frequency, And if we increase the frequency, we obviously would increase the power as well. But we had seen it earlier in rise and fall time calculations. We cannot increase our frequency beyond a specific value, because we have to keep in mind the rise and fall times as well. So we have to there should be a trade-off between increasing the frequency for power and also for the rise and fall time. So if we want to increase the frequency of our circuits, we have to keep in mind two different factors. One is our rise time and fall time, and the other one is our power dissipation. Obviously, if we have to reduce the rise time and fall time, we cannot obviously have a very slow circuit, so that we may wait for hours to complete the task. So if we want to increase the frequency, then we have to care for the rise time and fall times. So this is an end to our discussion for the inverter circuits. And from the next session, I will talk about the DC characteristics or DC analysis of our gates, and then we can find that how can we analyze our different complex circuits as well. So that's it for today. I will see you in next video, inshallah.